Oh, okay. It was because I pulled the length of this was. Oh. Okay, 1 second, one thing at a time. Okay. Hello?
Sorry. Okay, so good evening, everyone. Welcome Professor John Paul to the center. So Professor John Paul is going to be with us for nearly 22 days. And he is going to give a series of lectures on liquid crystals. And I'm sure this audience doesn't require any introduction about John Paul. So he's a well-known mathematician, has made significant contributions in many areas of applied mathematics, including calculus of variation, elasticity, and so on. So he was also the president of International Mathematical Union during 2003 to 6. And he's also currently the president of the Royal Society of Edinburgh. So welcome, Professor Paul, and over to you.
Well, thank you very much. It's been a bit postponed, this visit, due to the pandemic. But, I'm very happy to be here. And I should maybe say it's supported by the Royal Society, actually by a partly Indian benefactor, Yusuf Hamid. So okay, so now it's not a good idea to work on problems because they're popular, but this shows the number of papers which on MathSciNet which mention the word liquid crystals as a histogram against time. So you see that it's really increased incredibly since actually this first step here was due to a program that was run at IMA in Minnesota, which Jerry Erickson, one of the leaders in the field, started. So that made a big impulse, and then it has sort of more or less continued increasing ever since. Okay, so here's some of the topics I'm going to talk about. I'll give some kind of introduction to liquid crystals and phase transformations and the variables one uses to describe them, the alias order parameters. And then I'll talk about various theories, the Ozing-Frank theory, which is the oldest one, Landau-de Gennes and Onsager theories, which are sort of perhaps more popular with physicists now. I'll describe something called the singular bulk potential, and I will try to explain how these theories describe defects, which are something that's very common in liquid crystals. And at the end, maybe I'll have time to talk a little bit about smectics and thin films. Okay. So here's some sort of themes which will run through the talk and the talks. One is that function spaces are part of the model, not part of models in physics. I mean, this is not maybe a popular or comfortable thing to say. I mean, when we sort of, for example, derive the Navier-Stokes equations for a fluid, we tend to assume that everything is smooth. We get the equations, and then analysts start working on it and start applying function spaces and decide what sort of function space to look at the equations in. Of course, really the derivation should already have the function space in there, and the function space tells you what singularities you're going to allow. And if you change the function space, you will, in general, change the predictions of the model, which leads to the question of where the function space should come from. Maybe the answer to that is that it should come from some sort of atomistic to continuum process, where you derive some kind of continuum limit, and at the same time you derive the function space. So anyway, it's going to be very important that this sort of difference, the relation between different levels of description. So molecular versus continuum. There'll be order parameters of different dimensions. The higher the dimension of the order parameter, the more variables you have to describe something, then you should be able to do some kind of better job, but maybe the theory becomes too complicated, and so you can't use it. Sometimes simpler theories tell you more. And another sort of theme will be constraints on unknowns in variation problems. So we'll see that equality and inequality constraints, and we'll see that happening in these models of liquid crystals. So first of all, what are they? Well, they're an intermediate state of matter between liquids and solids. So they flow like liquids, but the constituent molecules retain some orientational order. And it's a vast industry. There'll be many liquid crystals in this room in your watches, on your computer displays, phone displays, and so on. And it's an absolutely huge industry. Just on the right here, there's maybe a somewhat old picture of a so-called bistable display. That's one which retains the image even when you turn off the electricity. So these are interesting technological devices. Okay, so there are various classes of liquid crystals. The three main types, or three main sort of possible phases, are nematics, polysterics, and smectics. Now, many liquid crystals consist of rod-like molecules. So here's a space-filling model, courtesy of Claudio Zanoni, who's one of the big experts in computations with liquid crystals, of two synthetic liquid crystal molecules. One's called MBBA, and the other is 5CB. Lots and lots of studies are done on these molecules, and you see it's color-coded so that the carbon atoms are in this light blue, and the hydrogen in the sort of the gray. There's a nitrogen atom there, and there's an oxygen atom there. So they're very small, 2 to 3 nanometers in length. So very difficult to see using microscopy. Okay. And I should say that the typical liquid crystals that are used in practical displays are mixtures of lots of different molecules, different kinds of molecules. Okay, now, depending on the nature of the molecules and the interactions between them and the temperature, the molecules can arrange themselves in different phases. So at a very high temperature, the thermal motion will agitate the molecules, so there'll be essentially no order of any type. And then the liquid crystal will probably be in an isotropic phase, so there's no orientational and no positional order. The positions or centers of masses of the molecules, well, I should say here, we already see something that's often done in pictures of liquid crystals, that the molecules are represented as ellipsoids. So of course, they're not ellipsoids, but even in some theoretical studies, they're taken to be ellipsoids. So there's no orientational order. So in other words, the long axis of the ellipsoid is pointing in random directions, and there's no positional order. So the centers of masses are also distributed in a random or uniform way. So here's a picture of 3 different phases of liquid crystals. The first one is on the left is the nematic phase. And there we see the molecules are more or less pointing in a certain direction given by this unit vector n. But otherwise, there's no sort of other structure. Now, these two are so-called smectic phases. This is smectic A, and the second one is smectic B. So here we have that the molecules still point more or less in a certain direction, n, but also they form themselves into layers, and the layer normals are another vector, m. And in smectic A, n is equal to m. In other words, the molecules are roughly speaking perpendicular to the layers. In smectic C, the molecules make an angle, a particular angle with respect to the direction of the molecules makes a particular angle with respect to the normal to the layers. So in the nematic phase, there's orientational but no positional order. That's smectic A, this is smectic C. Here's another phase, the cholesteric phase. And in this one, the molecules want to be, well, they want to be sort of pointing to the right on some plane here, and then as you move up, they gradually turn until they've gone through an angle pi, and then eventually an angle 2 pi, so they're back where they are, and there's a sort of characteristic distance for the the distance it takes to go through 2 pi. Now these three phases, the two smectic phases and the cholesteric phases, have orientational and some positional order because there are these layers. And the molecules, of course, are not static. They're jiggling around with under thermal motion, so they have time varying orientations. Now, as I mentioned, it's very difficult to see these molecules in say an electron microscope. So that's a bit different from solid crystals. So in solid crystals, you can use transmission electron microscopy to more or less see atoms, which appear as dots in these pictures. But that's because everything is arranged in a crystal lattice, so that enables you to do the imaging using transmission electron microscopy. But I've never seen any sort of electron micrographs of liquid crystals where you actually see these very small molecules. Maybe they exist, but I've never seen them. So the best you can do is to see a nematic phase, say, in a slightly different system. So this one on the left is called tobacco mosaic virus, and the virus forms these rods. And so you see that they more or less line up locally in some way. So it is pretty haphazard. And this one's quite interesting. This is carbo nanotubes. So if you arrange a carbon, you take lots and lots of carbon nanotubes, and you vary the various conditions. So in this picture on the left, it's sort of isotropic. They're sort of pointing in more or less any direction. And on the right, it's nematic. So you see that there's, for example, in this region, they're more or less pointing in this direction. So you can kind of see the fundamental objects in these slightly different situations. So the nematic phase typically forms when you cool the liquid crystal through a critical temperature, which we call theta critical. So, so we have a temperature. This is the temperature axis, and so for temperatures theta bigger than this critical temperature, theta critical, that's where thermal agitation takes over, and the material will be in its isotropic phase. And then when you reduce the temperature below theta critical, but maybe not too much, the nematic phase forms, and so the molecules begin to line up like my fingers in some sense. And then if you reduce the temperature still further, something else might happen. It might have another phase transformation to a say a smectic phase, or it might solidify, turn into a solid. Now for MBBA, which was the left-hand molecule of those two that I showed you, the temperatures would be 45 degrees C and 17 degrees C. So it forms a nematic in this temperature range. Okay, so here's a movie of the nematic phase forming in the isotropic phase. So the isotropic phase is in black, and now the temperature is being reduced. Oh shoot! A second. There we go. And you'll see the nematic phase appearing in the isotropic phase. This is off quite an interesting website where you can see lots of pictures of different things in material science. And what you see is also some interesting structure in the nematic phase. These are defects of one type or another, which we'll talk about as things go on. And this is in fact MBBA as well. Okay, now the use of liquid crystals in displays is actually quite complicated. It's amazing what's actually in these displays, and so the idea is this: you put the liquid crystal between two plates, and the plates are treated so that, say, on this bottom plate, the molecules want to line up in this direction shown by the black lines. And on the top plate, it's treated so that they want to lie perpendicular to that direction. So the two plates are parallel. And also, there's polarizers here which allow light through, which is polarized in this direction, and on the top plate allows light through that is polarized in the perpendicular direction. So when there's no field applied, what happens is that there's a sort of equilibrium solution of the liquid crystal, which we'll talk about, in which as you go from the bottom plate to the top plate, they gradually rotate, so that it's gone through an angle pi by 2 by the time you got to the top plate. And the light, if you propagate it down here, gets its polarization gets twisted by the liquid crystal, so that it goes through the top plate because it's polarized right, and then it gradually twists the polarization, and on the bottom plate it's correctly polarized, and so the light goes through. However, if you then apply an electric field vertically, then the molecules will want to line up to be parallel to the field, and then the polarization is not twisted by the liquid crystal, and so if the light comes in from the top, by the time it's got down to the bottom, it's got the wrong polarization, and the light is not transmitted. Okay, now I'm going to show you a simulation of this later, which is not as clean as this sort of picture. So how would one go about modeling these liquid crystals? So one natural thing to do, which I'm not at all an expert in, would be to use molecular dynamics. So for example, you can do a Monte Carlo simulation using an interaction potential between two liquid crystal molecules. And one such interaction potential is used as so-called Gay-Byrne potential. So the molecules are going to be represented by ellipsoids. So they look more like this, but we think of them as ellipsoids. And there'll be distances between the ellipsoids and different angles, orientation of the ellipsoids. And the interaction potential is some kind of anisotropic version of the Leonard-Jones potential that's familiar when one's considering pairs of atoms and molecules. So it's not important for us what the actual formula is, but there it is, the formula. So this is the interaction potential, Gay-Byrne, and there's there's a 12th power here. U is here's the U expressed in here, and the sigma is the contact distance between the ellipsoids, and the epsilon is the attractive well depth. So that's a bit like the Lennard-Jones potential as various constants floating around. Anyway, there is a complicated potential that apparently does quite a good job. And I want to show you a simulation of Zanoni's group of the twisted nematic display using molecular dynamics. So to understand the picture, the simulation, so there's a color code for the direction in which the molecules are pointed. So if they're pointed vertically upwards, it's blue. If they're pointed out of the screen, it's red. And if they're pointed in this direction, it's green. So, so you see that this is the initial configuration. So you see that the molecules want to be in this direction on the top face. That's the due to the treatment of those faces, and in this direction on the bottom face. So to actually do the simulation, so the simulation involves about 1 million molecules. This was 2009. No doubt you could do much better now. And you fix the orientations in this top layer so that you're applying the boundary condition that the molecules have to be pointing in this direction on the top face, and ditto on the bottom face. And as a sort of starting configuration, we put all the molecules pointing upwards in the middle, and we let the simulation run. So Newton's laws for molecular dynamics with that interaction potential, and what we're going to see is also a picture not only of the colors, so we see the orientations, but also of viewed from above, so we see whether the light gets transmitted or not. Okay. Sorry, that's wrong. Where's the simulation now? I've got to find the simulation. There we go. So on the right is looking down from on top, and here it's running it, and you see that now this kind of twisted configuration starts appearing. It's not very clear due to all this thermal motion, and you see that the light gets transmitted because it's formed this twisted nematic. And now we're going to turn on the field, and you see that makes the molecules want to be vertically in this direction here, and you see that because it's not twisted, the light does not get transmitted. So that's one of many simulations that can be done for liquid crystals. However, in this course, I'm going to consider continuum models. And so we're going to consider a nematic liquid crystal, which fills a container, or a liquid crystal that can take a nematic phase, that fills a container omega, so some bounded open region of R3 with a reasonable boundary, Lipschitz boundary, so it could be a cube or ball, for example. And I'm going to make some terrible assumptions here. So first of all, I'm going to consider only static configurations. So the fluid velocity is going to be 0. So I'm just going to be interested in the orientation of the molecules. Secondly, I'm going to suppose that the temperature is a constant. And thirdly, I'm going to suppose that there are no electromagnetic fields. So that's a really awful thing to do in terms of the applications. But it turns out that when you write down the energy functional for the liquid crystal, the electromagnetic fields, of course, they change what the energy minimizing configurations are, but the terms they add are sort of lower order terms. So the mathematical difficulty is essentially in the case when the electromagnetic fields are not present. So a first mathematical description of the nematic phase is to represent the mean orientation of the molecules by this unit vector field. So n is going to depend on x. X is a point in omega. So n of x is a unit vector, so it belongs to the unit sphere S2. And this unit vector field is called the director. So now the oldest and still very useful model is the Ozone-Frank model that uses as an unknown this director field. So it has a free energy functional I of n, which you get by integrating over omega a function w that depends on n and its gradient. And here is the free energy density w that depends on n, the gradient of n, and it's quadratic in the gradient of n. So we've got div n squared here, we've got the curl n, and there's a square, and there's a curl n here, there's a square, and here there are squares. However, there's a couple of places where n itself appears, n dot curl n and n cross curl n. So actually, if you make the assumption that w is quadratic in the gradient of n and satisfies appropriate invariance requirements, which are physically necessary, then you end up with this Ozone-Frank form. Now the Ki, so K1, K2, K3, and K24 are called the Frank constants. And they govern different modes of deformation of the liquid crystal. So the first one is associated with a splay deformation. So if my fingers with a liquid crystal, that's a splay. And the third one is associated with bend. So that's when the direction of the molecules is like this. They bend. So we'll see more about this as we go on. Now, the final term is a bit more complicated, but more interesting. It's usually called the saddle splay term. And it's a null Lagrangian. So if you calculated the Euler-Lagrange equations for this expression, which I encourage you to do, you can ignore the fact that n is a unit vector. You don't have to worry about that. You'll find that you just get 0 equals 0. So in other words, every n satisfies the Euler-Lagrange equations for this functional. So what that means is that if you integrate this over omega, that its integral will depend only on the values of n on the boundary. So, I mean, there's different ways of seeing this, but I mean, one way is to notice that this expression can be written as a divergence. So then you use the divergence theorem and you find that this integral is an integral is an integral over the surface. In just involving n and its tangential derivative. So if n is specified on the boundary, then the integral will only depend on the values of n on the boundary. So there's more sophisticated ways of doing it that don't involve having regularity on the boundary and so on. In any case, it's the integral of this last term. If we have boundary conditions in which we specify n on the boundary, will be independent of n. And so in that case, you can drop this term because all it does is add a constant to the energy, which is this integral. However, there are boundary conditions where this really does, where this integral really does depend on really does depend on n, and in that case, you need to keep this term. Okay. And recently, there's been a paper that seems to have got quite a bit of popularity. I was reading it over the weekend, and it is quite interesting. It sort of identifies this saddle splay term. It sort of Salinger decomposes it somehow into a splay, a twist, and a so-called double twist component. So there is an interpretation of this term in terms of sort of elementary modes of deformation. Okay, however, I wouldn't use that. Okay, so here's a fundamental energy minimization problem. We give ourselves some boundary conditions so that n on the boundary is some given n bar, which varies as you go around the boundary. And you have to find an n that minimizes the integral subject to those boundary conditions. So that's the question, can you do that? Is there such an n? What can you say about it? So here's the integrand again. And so an initial calculation that is interesting is to see when this W can be bounded below, which is the same as saying when it's non-negative. And so Ericsson showed, in fact, that W is bigger than or equal to 0 for all n, if and only if these inequalities hold. So K1 is bigger equal to K24 is bigger equal to 0, same for K2, and K3 is bigger equal to 0. So that's not a completely trivial calculation because it uses the fact that n is a unit vector. It's a little bit tricky, actually. Now, usually we'll assume the strict form of this whole, so we put strict inequalities everywhere. And those strict inequalities are necessary and sufficient for W to be bounded below by a positive multiple of the gradient of n squared. So this is the Euclidean norm of the gradient of n, so the sum of the squares of dni dxj, and some positive constant mu. So you can prove that by applying the Ericsson inequalities to an expression like this. Okay. Now, also, of course, n is bounded and W is quadratic in the gradient of n, so W is also bounded above by a constant times the gradient of n squared. So if the strict form of the Ericsson inequalities holds, W is bounded above and below by different multiples of the gradient of n squared. So that means that the natural space, the natural function space of the vector fields of finite energy is this Sobolev space. So it's written H1 of omega with values in S2. So it's the set of maps n from omega to S2, so the set of unit vector fields such that the integral of the gradient of n squared is finite. And gradient of n is defined in the sense of distribution, so it's allowed to take certain kinds of jumps, but not all kinds of jumps. We'll see more about that later. Now, more precisely, this is not very clear maybe as it's written, you can define H1 of omega S2 as the closed subset of this of the Hilbert space H1 of omega with values in R3. So that's a standard Sobolev space H1 of omega with values in R3. So it's a set of maps which are in L2 and their weak derivative gradient of n is in L2. And so if I look at the subset of H1, which satisfies that the absolute value of n of x is 1 for almost every x in omega, then that gives a rigorous definition of this Sobolev space. So there's the integrand again. Now there's some important identities. So first of all, the absolute value of curl n squared. So these identities involve all the terms you see. Is the sum of n dot curl n squared and n cross curl n squared. And the second identity is interesting. So it says that the gradient of n squared is the sum of all the terms that appear here, namely div n squared, n dot curl n squared, n cross curl n squared, and trace squared n squared minus div n squared. Of course, you could, if you want, cancel the div n squared with this div n squared. Okay, so these are important identities, and so that means that if K1 and K2 and K3 are all equal and equal to 2K4, to K2 times K24, that means that we have exactly K1 over 2 the gradient of n squared, right? And that's the so-called one constant approximation. So in that approximation, which is often used because it's for theoretical reasons, because it's much easier to handle than the general case up here. So then I of n is the energy functional associated with what are called harmonic maps. So you have the Dirichlet integral of gradient of n squared, but the important thing is that n is a unit vector. Right? So that's what makes it a non-trivial matter, even in this one constant case. Okay, now here's the first thing that, actually, this is the thing that first got me interested in liquid crystals. So n of, at least for many nematics, n of x and minus n of x are physically indistinguishable. Now it may be that individual molecules, you can tell what one end may be different from the other end. But statistically speaking, there's just as many, if you like, pointing upwards as pointing downwards. So the director, the mean orientation, n of x is physically indistinguishable from minus n of x. So you shouldn't really have an arrow here. You should have a double-headed arrow. Now, so it's better thought of as a line field, not a vector field. So, or that is a map from omega to the set of all lines through the origin. Now, a typical such line with direction plus or minus n, so it's a question of how you represent it, and it turns out that a good way to do it is to use the matrix capital M, which is n tensor n. So this is the matrix with components ni, nj. And the set of all such lines forms what's called the real projective plane, RP2. Now, smooth line fields need not be orientable. In other words, you can have a smooth line field such that it's impossible to assign a direction that turns them into a smooth vector field. So here's an example. So you can either think of this two-dimensionally or three-dimensionally. So this gray disk, if you think of it as a cylinder perpendicular to the screen, and all the directions of the of n are going to be in the plane of the screen. So on the left, we'll have so there's going to be a line field, right? So the line field specifies a direction, but not an arrow. So the line field is going to be like this. So I think it's essentially obvious what happens. They go around. These ones here just end to the end in the cylinder. Okay, so that's a smooth line field. So let's try and orient it. Okay, so what are you going to do? Well, to the left, I mean, we want to have a vector field that's smooth. Right? So on the left, we've got two choices. We can either have all the arrows pointing to the right, or all the arrows pointing to the left. Okay? So let's suppose that they point to the right. Well, if they point to the right, then they've got to continue pointing in this direction as you go around. And then by the time you got to the bottom, they're pointing in the opposite direction to these ones. And so in this blue region, you've got some discontinuity in the vector field. So that's an issue. It's an issue, and it leads to one way you can try to resolve it is by considering what I'll call an unoriented Ozane-Frank model. So this is a constrained version of the Landau-de Gennes model that we'll discuss later in the course. So M, we're going to take the variable as M, which is n tensor n, because that's the way you describe a line field. And you can write W of n and the gradient of n formally as some other function W tilde of M and the gradient of m, with W tilde quadratic in the gradient of m. In fact, so how do you do that? Well, the gradient of m has typical components mij, comma k. So that's d by dx k of mij. And so m is ni nj, so mij, comma k is ni nj, comma k plus nj ni, comma k. Now, if you multiply this by nj, you see you'll get a term ni nj, comma k nj. But nj comma k is d by dx k of a half of the norm of n squared. But n is a unit vector, so the norm of n squared is 1. So that is 0. And so you see that mijk nj is ni comma k. So wherever you see in the Ozane-Frank energy the gradient of n, you can replace it by mij comma k nj, and then you find that wherever nk appears, you get an nj nk, and that is just a component of m. Okay, so you can express all the terms, in fact, in W in terms of capital M and the gradient of capital N. So, for example, in the one constant approximation, k1 over 4, the gradient of m squared is k1 over 4, and I'm going to write I write mij comma k, and then mij comma k again, and you see that, for example, this times this gives you ni, which is 1, because n is a unit vector, times nj comma k, so that's gradient of n squared, and you get another one from this times this, and then the cross terms go away because you get an nj comma k, which is 0 because n is a unit vector, and this one times this gives you an n. So this one times this gives you an ni, gives you nj comma k, nj ni comma k. So that was times this one times this one gives you an ni comma k, which is 0. Okay. So you get 2 gradient n squares, and that makes the quarter turn into a half. So you get exactly the same kind of form, except M now is this matrix. So now, if you let RP2 be the set of M 3 by 3 matrices, which are of this form, n tends to n, and a unit vector. So you can write it equivalently, if you like, as the set of M which are symmetric, whose trace is 1, such that the norm squared of M is 1 and the determinant of M is 0. It's a different way of writing it without introducing the N explicitly. And then you have an unoriented energy minimization problem. Now you've got to find a capital M, taking omega to RP2, that minimizes I of M, which is the integral of this new energy density, W tilde of M and gradient of M, subject to suitable boundary conditions. And then the natural function space is H1 with values in RP2. But there's something interesting happens. There's this theorem proved by Petuel and Chiron and also myself and Zarnescu, that if omega is simply connected and M is in this space, then you can orient it, right? There is an N in H1 with N is equal to N tensor N, right? So in the example I gave before, the region was not simply connected. But if the region is simply connected, then you can orient any line field in H1. So the conclusion of that is that the Ozane-Frank model and its unoriented version are equivalent if omega is simply connected. However, they're not equivalent if omega is not simply connected. And here's an example which modified from Zarnescu and myself. So showing that the minimizing M in the unoriented theory may not be orientable. So here's the example. So omega is going to be this green two-dimensional region, which is kind of a stadium with two holes removed, crossed with the interval -1, 1. So that -1, 1 goes into the screen. Okay? So the distance between the holes we'll call 2 delta. So we see we've got various surfaces of this domain. There's the flat surfaces in front and at the back. There's the curved surface around the outside, and there's the cylindrical surfaces of the insides of these cylinders. So now I'm going to impose some boundary conditions. So M is N tensor N as usual. So the boundary conditions are going to be that on the outer boundary and on the flat parts, so in front and behind, the director has got to be in the x1, x2 plane, in the plane of the screen, right? So it can be on this front face, it can point in any direction it likes, but it can't point into the screen at all. And so those are quite reasonable boundary conditions that you can impose in practice. And now on the inner curved boundary, so the inner surfaces of these two cylinders, so that's D1 as labeled here, and union DD2 crossed with -1, 1, which is the interval into the screen. I'm going to impose what's called weak anchoring. So you'll see what I mean by that in a second. And the functional is going to be this. I of M is going to be take the one constant case, so K1/4 integral gradient M squared, and this is the weak anchoring on the inner curved surface boundary. So here's it's an integral over that surface times N dot mu squared. All right, so that's if you like M mu dot mu. So it's expressible in terms of N. Okay, and you see that in order to, if K is large, then in order to minimize this, you want that N is parallel. That N is parallel to plus or minus nu. Okay, so it's trying to make the director point in the direction of the normal. So that's why it's called. I could have imposed that it points exactly in the direction of the normal, but it wouldn't be so easy to do the calculation there. Okay, so that's the minimization problem. I want to minimize this integral subject to these boundary conditions that I've specified. So now it's possible to orient those boundary conditions. So I could, for example, I can orient them in this way so that the vector goes around like this. on the front, you just interpolate between these directions. So these boundary conditions are orientable. So the question is whether the minimizer, subject to the boundary conditions, is orientable or not. So now, if it's orientable, the energy is this, right? So I of n is k1/2 integral gradient n squared, and then minus the same term. Okay, so let's imagine that we've got an n that matches the boundary conditions. Now, if it's orientable, we're going to have to either have the boundary condition going up around this way clockwise, or the other possibility is to go around anti-clockwise. It comes to the same thing. So let's suppose that we've got an n, it's orientable, and that on the boundary it goes clockwise like this. So then as you move along a line horizontally, you see it's got to move from pointing vertically upwards to pointing vertically downwards. Okay, so you can estimate the energy. It's a sort of one-dimensional calculus variations problem. You can estimate this energy along this line. Okay, so along this line, the integral of the gradient of n squared is bounded below by some number. So that means that if the distance if this 2 delta is sufficiently large, the energy of any orientable deformation is going to be huge, because across each line here, you're going to get a certain amount, and so that'll be integrated. It'll be multiplied. That certain amount will be multiplied by the distance between the cylinders. Now, there'll be a bit of energy associated with what happens up here and down here, but that's a finite amount of energy, which is just a certain amount, right? However, you can find a line field which matches the boundary conditions, which has less energy, right? So here it's shown. So in the middle, you see the line field is vertically upwards. It's a constant. So the gradient of the line field is 0 in this region. So it doesn't count anything at all. And up the top, there's a little bit, and down the bottom, there's a little bit. But so that shows that this will have, if the distance between the cylinders is large, then this configuration, which is not orientable, will have less energy than the orientable one. So in short, so that's what I'm saying. So in short, the constrained theory is not equivalent to the Osing-Frank, to the unconstrained theory, if omega is not simply connected. So this is a little issue that you have to worry about. However, from now on, we consider so what is the tradition here? Do I speak for 50 minutes, in which case I've already spoken for 50 minutes, or
it's
1 hour? What is the?
1 hour.
Okay, we'll go for 1 hour, so I'll work on another 5 minutes. So from now on, we're going to consider the standard oriented Osing-Frank model with this energy and boundary condition where n is specified on the boundary. So let's suppose that we've got a minimizer of this problem, and we take any smooth map, not necessarily a unit vector field. Well, in fact, it won't be a unit vector field because I want it to be 0 on the boundary. So a smooth vector field which is 0 on the boundary. And then I look at nx plus epsilon mx divided by its norm. So that's a unit vector field. And on the boundary, it is equal to n of x. So it's a unit vector field, but the norm of it is 1, of course. And so here on the boundary, it satisfies the same boundary value as n does. So formally, then you can calculate. You can put n epsilon in here, and you take the derivative with respect to epsilon. So if n epsilon is a minimizer, if n is a minimizer, then then the derivative of this with respect to epsilon and epsilon equals 0 should be 0. So what happens when you take the derivative? Well, you have to know what the derivative of n epsilon is with respect to epsilon. That we'll see that in a second. But you're going to have to take the derivative of w with respect to n and multiply it by the derivative of n epsilon with respect to epsilon, and then you're going to add the derivative of w with respect to gradient of n, and then multiply that by the gradient of the derivative of n epsilon with respect to epsilon. So what is the derivative of n epsilon with respect to epsilon? Well, it's p of nx mx, where p is this projection. So p of n is identity minus n tends to n. So doing what I just said, you take the derivative with respect, well, take this one first. You take the derivative with respect to n, and I multiply it by this derivative, so there it is. And then I take the derivative with respect to the gradient of n and multiply it by the gradient of this guy. And n, so that's got to hold for all smooth n that are 0 on the boundary. And that's what's called weak Euler-Lagrange. I'll write it as WEL, the weak form of the Euler-Lagrange equation. So now if you integrate by parts and use the arbitrariness of n, you formally obtain this Euler-Lagrange equation, that the identity minus n tends to n times the usual Euler-Lagrange equation, so the divergence of dw with respect to gradient of n minus dw dn is 0. So the fact that n is a unit vector has the effect of multiplying on the left the usual Euler-Lagrange equation by this projection. And that's so what is that? Well, that's called the Euler-Lagrange equation. Well, it's a second order. It's a second order nonlinear PDE. It's second order because formally, if you carry out this differentiation, you're going to get a second derivative of this times second derivatives of n. So it's a second order nonlinear PDE is nonlinear because W is nonlinear, and you have to solve it, and because it's a system of PDE. So n is a vector field, right? So this is three equations, three nonlinear equations, and you have to solve them subject to the pointwise constraint that n is a vector field. Okay, so now another way you could think of this is to use Lagrange multipliers. You could take I of n, and then you subtract a Lagrange multiplier lambda of x times the norm of n squared, and then you would get this form here. That this is equivalent to what I just wrote. The usual Euler-Lagrange operator is equal to a Lagrange multiplier depending on x times n. Okay, so that's exactly the same as this form. Okay, so that's obviously a quite difficult set of equations to try and analyze. So how can we solve them? Well, let's find out next time how we can solve them. Stop there, actually.
Okay, next questions. Where do the boundary conditions come in?
So where do the boundary conditions come in the?
When we solve for.
Yes, of course. Yes, we have to solve. You're absolutely right. We have to solve the equations also subject to the boundary conditions. So n has got to be. So indeed, yes.
Okay, so we will meet on Wednesday.
Wednesday. Okay.
So you want to go?
Yeah, because today just
Yeah, so there are two people who are coming.